So in this video, we're going to talk about shape and volume, and we'll start by focusing on shape. So in the context of engineering and mechanics, the shape is important because it influences structural stability and load distribution. So we can consider a few different examples. The first are triangles. Triangles are often employed to provide strength and rigidity that helps prevent deformation. Then we have arches, which efficiently distribute weight in order to reduce structural stress. And then lastly, we have cylinders, where cylinders are used to resist bending and provide uniform load-bearing support. So we can understand this a little bit better still by considering two different examples. The first here on the left, we see we have three different shapes, and we can consider their stability in terms of how difficult it would be to flip one shape over. So the left and the right shape share something important in common in this context. Because of their shape, they have the same center of mass, here essentially just in the middle. Now compared to the middle shape, which has a much lower center of mass, this means that they are going to be far less stable. Again, speaking about stability in the context of how difficult it is to flip one of these over. So you can see again in this very simple example that the shape plays a pretty significant impact in the stability of different structures. Now let's take this to a more real-world, practical example, and that's in the shape and the construction of a dam. So in this case, we can see we have a concave dam. So concave dam refers to a dam in this shape where it's essentially bulging forward. Now this isn't the only way to construct a dam, but in many instances it is the best way, and again this is fundamentally because of the shape. In this configuration, we see a lot of the force not in the center of the dam, but instead towards its sides. And the effect of that will be to essentially compress the dam's material towards itself into each other, such that the dam is stronger. So actually by leveraging the shape, you can reinforce the structural integrity, the stability, and that ultimately comes through an efficient manipulation of the load distribution. So now let's shift focus to the volume. So the volume measures the space that an object occupies, and it's calculated differently for each distinct shape. So let's consider two important examples, the first of which being a cube. So to calculate the volume of a cube, you multiply the length by the width by the height. But because a cube is a cube, and all of the sides are of equal length, we can express this more simply as the cube of the length of one side. Now, if we compare this to a cylinder, we see something quite different. In this case, we calculate the volume by multiplying the base area by the height, which is expressed as pi r squared h. Pi r squared is what's encompassed by the base area, so this is essentially just the area of a circle, so this is the bottom of a cylinder, and then we simply have the height of that cylinder. Now this brings us to a discussion of the displacement. So displacement occurs when an object is submerged in a fluid, pushing aside a volume of liquid that is equal to its own volume. And this is what we see in this image on the right here. On the left portion of the image, we see a graduated cylinder with some volume of water, and outside of that cylinder, we see this bolt. Now in frame B of the image, the bolt is no longer outside of the graduated cylinder. It's now on the inside. And in this case, the increase in volume we see going from frame A to frame B is equal to the volume of the bolt. Now, you can imagine why this is so useful. If you were to be told to measure the volume of this bolt, it'd be quite challenging. It doesn't have such a simple formula like that of a cube or a cylinder. So this can be a very easy and reasonably accurate way of measuring the volume of difficult to measure objects. Now, displacement also plays a very important role in the buoyancy. An object's buoyancy depends on the relationship between its weight and the weight of the displaced fluid. So for example, we see in frame B of the image that this bolt is not floating, it's sinking, it's not buoyant enough. So that means that the weight of the volume displaced is less than the weight of the object. If that were not true, it would be sitting here, floating at the surface. So now let's look at the everyday mechanical relevance of shape and volume through a few examples. The first is storage containers, which are designed with a specific shape in order to maximize volume and conform to storage facilities. Of course, typically you want to store as much as possible if you're using a large storage container. And of course, you also need to conform to the space. It needs to fit, it can't get in the way, it can't obstruct other operations. So the shape is very important. Another common example is that of ship hulls, which use displacement principles to stay afloat. So the way a ship actually is able to float is its hull displaces an enormous volume of water, and the weight of that water is greater than the weight of the ship, greater or equal to the weight of the ship. And again, this is what allows it to stay afloat. Then we have measuring containers, which rely on precise volume calculations for accurate measurement. Now, on the right here, we can consider an interesting example. We see two cylindrical containers that are quite similar, except A, this left container, is narrower and taller, whereas B is wider and shorter. Now, you might think, well, that event essentially cancels each other out. There's a slight difference in the y, there's a corresponding difference in the x, and therefore we should expect them to have the same volume. But this is not the case. Actually, B, which is double the width but half the height, has twice the volume. So looks can be deceiving in this context, and it's important to carefully consider the volume of a specific shape that you're working with. Now, here on the left, we have something else. We have three different shapes, and if we're asked to consider which has the greatest volume. Now, these aren't particularly irregular shapes. You could find or determine the formula to calculate the volume for each, do so, and compare those values. But you can actually simply imagine superimposing each of these into one another. You could place C into B, and you could place B into A, which means that A has the greatest volume and C has the smallest volume. So let's summarize some of the key points from this lesson. First of all, shape is important because it influences structural stability and load distribution, among other considerations. We provided three important examples, the first being triangles, which provide strength and rigidity to prevent deformation, arches, which efficiently distribute weight to reduce structural stress, and cylinders, which resist bending and provide uniform load-bearing support. Then we shifted the discussion from shape to volume, and said that volume measures the space that an object occupies, and it's calculated differently for different shapes. This led us to a discussion of the displacement, which occurs when an object is submerged in a fluid, such as water, pushing aside a volume of liquid that is equal to its own volume. And then lastly, we related this to an object's buoyancy, which depends on the relationship between its weight and the weight of the displaced fluid. If the weight of the object is greater than the weight of the displaced fluid, well then it will sink. And if it's not, then it will float.